I show here the research octane numbers for the isomers of hexane. Normal hexane has a research octane number RON of 30. 2-methylpentane, the RON is 74.5. 3-methylpentane, the RON is 75.5. 2,2-dimethylbutane, the RON is 94. And for 2,3-dimethylbutane, the RON is 105. The mono and di-branched isomers are preferred as blending components for high-octane gasoline. And in industrial practice, the demand for high-octane gasoline is met by having the alkane isomerization process, in which a feed mixture consisting predominantly of the normal hexane isomer is isomerized in a reactor with a modernite or MFI catalyst, and the reactor product consisting of a mixture of hexane isomers is separated using LTA5A zeolite that essentially sieves out the linear isomer, and the linear isomer is recycled back to the reactor. The raffinate phase consisting of the monobranched isomers 2MP, 3MP, and the dibranched isomers 2,2-DMB and 2,3-DMB are incorporated into the gasoline pool. I discuss in this presentation an alternative to this conventional alkane isomerization process, in which both the reaction and separation steps are combined into a single unit with MFI catalyst. Let's see how that works. In order to appreciate the use of MFI zeolite both as a catalyst and as a separation agent for the alkane isomerization process, let us examine the unary isotherms of normal hexane, 3-methylpentane, and 2,2-dimethylbutane in MFI zeolite at a temperature of 362 Kelvin. These are the configuration bias Monte Carlo simulations for the unary isotherms. The red circles are for normal hexane, the blue squares are for 3-methylpentane, and the green triangles are for 2,2-dimethylbutane. We see that the normal hexane has a saturation capacity of about 8 molecules per unit cell, whereas the mono and di-branched isomers, the saturation capacity is approximately 4 molecules per unit cell. To understand these differences, let us look at snapshots showing the location of NC6, 3MP, and 2,2-DMB within the straight and zigzag channels of MFI zeolite. Normal hexane can align itself either along the straight channels and or along the zigzag channels with equal ease, and the saturation capacity is 8 molecules per unit cell, because the length of a normal hexane molecule is equivalent to the distance between two adjoining intersection sites. 3-methylpentane, the monobranched isomers, prefers to locate at the intersections, and there are 4 intersection sites per unit cell, and therefore the saturation capacity is limited to 4 molecules of 3 MP per unit cell. The same holds for 2,2-dimethylbutane, which also prefers to locate at the channel intersections. And since there are 4 intersection sites per unit cell, the saturation capacity is limited to 4 molecules of 2,2-DMB per unit cell. Here are configuration bias Monte Carlo simulations for mixture adsorption for an equimolar mixture in the gas phase consisting of normal hexane, 3-methylpentane, and 2,2-dimethylbutane. We see that with increasing bulk fluid phase fugacity, this is the total fugacity of the gas mixture, the adsorption gets increasingly in favor of the normal isomer because of entropy effects that favor normal hexane that has the higher saturation capacity. Both monobranched isomer 3MP and 2,2-dimethylbutane, the dibranched isomer, are entropically challenged, and due to the entropic penalty, they lose the battle for occupying vacant sites with increasing bulk fluid phase fugacity. And at post-saturation, the mixture adsorption is almost completely in favor of the normal isomer. Watch also my presentation, Packing Effects in Mixture Separations, on my YouTube channel. So the message that emerges here is that the mixture adsorption favors the linear isomer, and the monobranched and dibranched isomers are entropically challenged. Let's examine intracrystalline diffusivities of the hexane isomers. Within the intersecting channel structures of MFI zeolite, the channel dimensions are 5.5 angstrom in size, and the normal hexane is less strongly confined within these channels than the monobranched and dibranched isomers, and the diffusivities decrease by 1 to 2 orders of magnitude with increased degree of branching. Therefore, the intracrystalline diffusion favors the linear isomer and disfavors the monobranched and dibranched isomers. Now, with this background on mixture adsorption and intracrystalline diffusion, let us proceed to examine how a isomerization reactor will work for the alkane isomerization process. And in this reactor, we use MFI catalyst. With the background information on mixture adsorption and intracrystalline diffusion, let's proceed with the calculations and simulations of a fixed bed reactor packed with MFI catalyst. For background on the theory and simulation detail, I refer you to my paper published in 2017. The feed mixture to the reactor consists of a mixture of NC6, 3MP, and 2,2-DMB, 1, 2, and 3 components. The partial pressures are 1000 Pascal for normal hexane, 1 Pascal for 3-methylpentane, and 1 Pascal for 2,2-dimethylbutane. The reactions for isomerizations are reversible. We have two reactions, reaction of NC6 to produce 3MP and the isomerization of 3MP to produce 2,2-DMB. The forward and backward reaction rates are considered to be linearly dependent on the molar loadings within the catalyst. The forward reaction rate constants are both taken to be 0.01, and the ratio of the forward to backward reaction rate constants are taken to be factor 2 for both these reactions. Based on the information on intracrystalline diffusion coefficients I showed in the previous slide, the ratio of the Maxwell-Stefan diffusivity for normal hexane D1 divided by the square of the crystallite radius for MFI catalyst is taken to be 2 times 10⁻⁴ per second, and for 3MP it's 2 times 10⁻⁵ per second, and for 2,2-DMB it's 5 times 10⁻⁶ per second. We present in the next slide the simulation results for the data inputs as shown here. These are the simulation results for the gas phase concentrations at steady state conditions for the fixed bed reactor packed with MFI catalyst. This is the normal hexane molar concentrations in the gas phase along the distance plotted as a function of the distance along the fixed bed reactor. The blue line shows the molar concentration of 3-methylpentane, and the green line shows the molar concentration of 2,2-dimethylbutane. There are definite advantages of operating the reactor in a transient mode, and this becomes obvious if we examine the gas phase molar concentrations as a function of a parameter that is linked to the time. So instead of plotting the time, I plot the parameter F0 that represents the molar flow rate at the inlet to the reactor in moles per second times the time in seconds divided by the mass of the catalyst in kilograms. So the x-axis as the units of moles per kilogram. During the initial transients, we see that the gas phase exiting the reactor consists predominantly of the 2,2-dimethylbutane that has the lowest diffusivity, a factor 40 less than that of normal hexane, and therefore the normal 2,2-dimethylbutane that is produced within the catalyst gets ejected from the catalyst particles into the gas phase and can be collected in the from the gas mixture exiting the reactor. So at this time interval, none of the normal hexane has exited the reactor, and the products are predominantly 2,2-DMB and 3MP. So if we operate in a transient manner, the fixed bed reactor also acts as a separator, and these two components can be removed and incorporated into the gasoline pool. For further background details, I refer you to my paper published in 2017.